For more than 3 million years, long before humans traced coastlines on maps or built cities along tranquil bays, the oceans themselves behaved like a living creature with a pulse, surging upward by tens of meters in surprisingly short bursts, then draining away again, as if Earth were quietly inhaling and exhaling through its frozen lungs, leaving shorelines stranded far from where they once stood. And the mystery that puzzled generations of geologists was why these rises and falls happened in giant rhythmic pulses rather than in slow, predictable drifts. Quick summary of script. In this story, we follow the birth of the world's great ice sheets, the astronomical rhythms that paced their growth, the greenhouse gas feedbacks that magnified them, the catastrophic meltwater floods that reshaped continents, and the strange turning point when the planet shifted from gentle 40,000-year ice pulses to brutal 100,000-year collapses that sent sea levels racing up and down like a global tide gone mad. Flow straight into the story, no extra headings. So we begin by easing into the early Pliocene, a warm world around 3 million years ago, when Earth was lush, coastlines were flooded, and global temperatures were several degrees higher than today. Yet even in this warm age, a subtle, almost invisible shift was underway, as the planet began a long cooling trend that would eventually give birth to vast ice sheets across the northern hemisphere. And although ice was present in Antarctica, the North still lacked the great continental masses of frozen water that would one day carve the sea level record into deep, dramatic swings. The first hint of something unusual came in marine sediments near ancient coastlines, where scientists found that fossilized shorelines and coral terraces stood far above present sea level, while other layers recorded times when the sea had withdrawn dramatically, revealing that early in this 3 million year journey, the seas were already beginning to rise and fall in patterns that were too regular, too large, and too rhythmic to be caused by tectonics alone. As the cooling intensified and the atmosphere thinned itself of greenhouse gases, ice began to accumulate in scattered patches across northern Canada, Greenland, and parts of Siberia. And this small but persistent buildup began tugging at global sea levels like a quiet thief, removing water from the oceans grain by grain, lowering them by tens of meters in pulses that matched periods of cooling, while warmer intervals brought rapid melting and equally rapid flooding of coastlines. These early oscillations were not yet the brutal ice ages of later times, but they hinted at a world where water responded to temperature with astonishing sensitivity, and where each degree of warming or cooling could shift shorelines by distances that would dwarf anything humans have ever witnessed. While early humans did not yet exist to see these changes, the Earth itself felt them deeply. River valleys carved new channels as sea levels fell. Continental shelves became vast plains where forests and grasslands sprouted, and as soon as the water returned, these landscapes drowned again, locking entire ecosystems beneath shallow seas. Scientists studying these transformations discovered that the pulses aligned with a repeating astronomical rhythm, a subtle tilt in Earth's axis, the obliquity cycle, occurring every 41,000 years. And this rhythm nudged temperatures up and down just enough to melt or expand the northern ice patches. The early sea level pulses were therefore not random. They were the heartbeat of a planet adjusting to the first stages of a cooling trend that would eventually transform everything from ocean chemistry to the evolution of early hominins. But even as these pulses occurred, the planet remained warmer than the deep glacial cycles that would follow. And during warm intervals early in this 3 million year journey, the seas could rise tens of meters above modern coastlines, flooding continental margins and drowning river estuaries under warm, shallow waters that teemed with marine life. This warmth created a world where small changes in temperature meant enormous changes in sea levels, because the young northern ice sheets were unstable, sensitive, and easily melted, and every time they collapsed, they poured unimaginable quantities of fresh water into the oceans, raising sea level faster than most coastlines could adapt. These dramatic transitions were recorded in coral reefs that tracked the height of ancient sea surfaces, in deep-sea oxygen isotope records that measured ice volume like a frozen diary, and in uplifted coastal terraces that preserved the shape of ancient shorelines like the rings of a planetary tree. The data showed that these early fluctuations were part of a larger cooling story that would eventually pull Earth into the Pleistocene ice ages, But during this early stage, the changes were already large enough to transform entire ecosystems repeatedly, drowning habitats, exposing others, and creating times when animals and plants had to migrate vast distances simply to survive. As the rhythm continued, the ice sheets expanded in fits and starts, and each expansion locked away more water, amplifying the downward pulses of sea level, while each melting period returned that water to the oceans, raising sea levels by dozens of meters in what, for geological time, counted as sudden surges. These early pulses mattered because they revealed a deep truth about Earth's climate engine: that the oceans were not passive, that they responded quickly, and that sea level was the ultimate storyteller of ice, temperature, and orbital rhythms that governed the planet in slow but powerful cycles. The drops exposed continental shelves nearly the size of entire countries, while the rises erased coastlines and forced rivers to redraw themselves. And this repeated reshaping of the Earth would later influence early human migration patterns, opening and closing land bridges like doors that connected continents only temporarily. Even in this first stage of the narrative, the birth of the earliest ice-driven pulses, we see the framework for everything that will follow. The interplay of ice sheets growing in the north, the astronomical cycles pacing their expansion, the greenhouse feedbacks amplifying every shift, and the key role of water as both a recorder and a messenger of global climate change. The sea rose and fell because Earth's climate was entering a new era, and the ocean surface was simply the most sensitive place to watch the transition unfold. These first pulses created a world that was always in motion, always rearranging itself, and always preparing for the even larger, more dramatic swings that would come later, turning the next 3 million years into a long, breathing cycle of ice and water moving in slow, gigantic waves across the face of the planet. The birth of the Great Northern Ice was not a single moment, not a sudden snap into a frozen age, but a slow gathering of cold that began as faint scattered patches across high plateaus and ended with massive ice fields stretching thousands of kilometers. And to understand how these expanding bodies of frozen water sculpted the earliest dramatic sea level drops, we follow the quiet emergence of glaciation in the northern hemisphere, as Earth cooled further around 2.7 to 2. 5 million years ago, when the climate slipped decisively into the Pleistocene and the seas began responding with deeper, sharper pulses. Ice had existed on Antarctica for tens of millions of years, but the North was unstable, sensitive, and uniquely positioned on vast continents where snow could accumulate year after year, transforming from soft powder into dense, ancient ice that locked away hundreds of trillions of tons of water, lowering global sea levels by tens of meters, even in these earliest phases of expansion. As temperatures fell, snowfall began to exceed summer melt in regions like Baffin Island, the Yukon, and the high Arctic. And every winter added layers of snow that summers grew too weak to erase, creating a feedback that made each new layer more permanent than the last, slowly thickening into the first glacial domes of the Laurentide and Eurasian ice seeds. These glacial seeds were tiny compared to the giants they would one day become, but they were powerful enough to change sea level measurably, pulling water out of the oceans in slow pulses as ice accumulated, and then returning it just as dramatically when warming intervals arrived and the young ice sheets melted with surprising speed. Geologists examining sediment cores from the North Atlantic discovered layers of coarse debris, rock fragments dropped from melting icebergs, that matched these early pulses precisely, offering some of the earliest physical markers of how the northern world was beginning to freeze. The formation of ice in the north mattered enormously for sea level because of geometry. The continents provided vast flat surfaces at the right latitudes for snow to accumulate, while Antarctica, though already frozen, had limited additional capacity to store more ice, meaning any global cooling now directly translated into huge new volumes of water being trapped far from the oceans. During the early Pleistocene, each time the northern ice seeds expanded, sea levels could fall by 10, 20, even 30 meters, exposing continental shelves in Europe and North America, and dramatically altering coastlines that had remained stable for millions of years. Forests migrated southward, grasslands expanded into places that had once been shallow seas, and river systems lengthened as coastlines retreated outward, cutting deeper channels to meet distant ocean basins. Yet these early pulses were not only about ice volume, they also revealed how unstable the young ice sheets were. Fresh snow reflected sunlight, cooling the surface further and allowing even more snow to accumulate, but summers could still be warm enough during certain orbital phases to melt huge portions of the growing glaciers in just a few thousand years, causing rapid sea level rebounds that flooded back over the exposed shelves. This instability meant the oceans never stayed still. The waters advanced and retreated repeatedly, reshaping marine ecosystems, drowning ancient coastlines, and carving underwater terraces that modern oceanographers still map today. Coral reefs followed the rising seas upward, creating stair-step structures that now sit on uplifted coasts like Barbados and Papua New Guinea, each step marking a time when sea level paused temporarily during one of these early cycles. At the same time, dust blown from newly exposed glacial plains settled into ocean sediments, providing a second line of evidence. The more dust present, the lower the sea level had been, since expanded ice sheets created barren landscapes ripe for wind erosion. These dust records align closely with oxygen isotope data from foraminifera, tiny marine organisms whose shells hold a chemical signature of global ice volume, together forming a precise record of how the early northern ice sheets produced predictable repeated sea level swings. Even though the northern ice sheets were still young, their influence was already enormous, and this sensitivity to even small temperature shifts set the stage for far more dramatic fluctuations in later eras. The significance of the northern ice birth also lies in its timing. Around 2.6 million years ago, Earth officially entered the Pleistocene epoch, often called the Ice Age epoch, and this transition marked not just a cooling event, but the beginning of a new climate system in which ice sheets would continually grow and collapse in response to orbital cycles. Before this point, sea levels had moved up and down with warmth and cold, but the range of motion was modest. Once the northern ice began to expand, the amplitude of sea level change increased dramatically, creating drops large enough to expose land bridges that would later influence the migrations of early hominins, animals, and plants. Although humans would not emerge for hundreds of thousands more years, these early oscillations were already shaping the geography of the world our ancestors would one day inhabit. As the northern ice thickened into true continental glaciers, they became powerful agents of climate change themselves, cooling the atmosphere through increased reflectivity and altering wind patterns that redistributed heat across the globe. These changes reinforced. In these early stages, however, the sea level waves were still relatively smooth compared to what would come later. The northern ice sheets were not yet tall enough or heavy enough to destabilize dramatically. Their collapses were substantial, but not catastrophic, and the melting, though fast in geological terms, did not produce the sudden megafloods associated with later deglaciations. Still, the world was learning a new pattern, and the oceans responded faithfully. Each cold period pulled them downward, each warm pulse lifted them upward, and the amplitude of this dance grew larger as the ice gained mass year after. These early fluctuations also provided important clues for modern climate scientists. By studying how sensitive sea level was to small temperature changes in the early Pleistocene, researchers learned that the oceans respond non-linearly to warming, meaning a small shift in global average temperature can produce disproportionate changes in ice volume and sea level. This insight has profound implications for today's warming world, but in the context of our long story, it serves as a reminder that even the very first northern ice sheets were potent drivers of sea level change, capable of reshaping continents before they ever reached their maximum extent. By the time the northern ice sheets had become stable enough to survive multiple cooling cycles, sea levels were already falling farther and faster than they had in millions of years, and the young Pleistocene Earth had fully entered a new climate regime where the position of a coastline at any moment was merely a temporary suggestion rather than a permanent boundary. These dramatic early drops, driven by the birth of northern ice, set up the long chain of events that would later change the rhythm of Earth's climate, deepen the cycles, and create the immense sea level surges and collapses that define the last 3 million years. Pulses we will follow deeper in the sections to come. Warm peaks, sudden floods. This was the other half of the great heartbeat that defined the early Pleistocene, because every time the young northern ice sheets reached their fragile maximum and the planet slipped into one of its brief interglacial warmings, the world responded with astonishing speed as walls of ancient ice collapsed, oceans surged forward, and sea levels rose in abrupt, powerful floods that transformed coastlines so dramatically that entire continents seemed to inhale water in a single breath. These warm intervals were short-lived glimmers compared to the long, cold stretches, but they carried enormous power, because during each warming pulse, temperatures increased just enough to cross melting thresholds in the ice sheets, and once these thresholds were crossed, massive volumes of frozen water poured into the oceans, sometimes raising global sea level by tens of meters over just a few thousand years, a blink in geological time, yet enough to drown valleys, erase deltas, and redraw continental shelves entirely. The reason these warm peaks produced such sudden floods lies in the physical structure of the young ice sheets, which were not yet as stable or thick as the behemoths of the later Pleistocene, and these early glaciers often sat atop bedrock slopes that encouraged rapid retreat once melting began. When summers grew warmer or lasted slightly longer due to orbital patterns, meltwater pooled beneath the ice, lubricating the base and accelerating the collapse, allowing enormous ice masses to break apart and slide seaward in a chain reaction that amplified itself with each passing season. As the ice retreated, sea levels rose rapidly, not gradually, and the effect was global. Coastal plains that earlier glaciations had exposed were suddenly submerged, ancient beaches drowned under rising tides, and ecosystems forced to abandon land that had existed only briefly during colder intervals. Marine isotope records show these warming peaks clearly. Oxygen-18 ratios drop sharply, indicating reduced ice volume and warmer oceans, and these drops align perfectly with coral reef terraces, showing higher sea levels during interglacial phases. One of the earliest major warm pulses occurred around 2.4 million years ago, when a sudden reduction in northern ice volume caused sea levels to rise by more than 20 meters, flooding regions from the Gulf Coast to the Mediterranean and forcing shorelines thousands of kilometers away to migrate inland. While humans would not appear for hundreds of thousands of years, this early instability in sea levels created patterns that would later influence migration corridors, because the flooding erased lowland plains that future hominins would eventually cross, replacing them with shallow seas that stayed submerged until the next cooling cycle. Warm intervals were shaped by more than temperature. Greenhouse gases also played a crucial role. During cold periods, carbon dioxide was drawn down into oceans and soils, but during warming peaks, as ice melted and global photosynthesis patterns shifted, CO2 levels tended to rise, amplifying the warming and accelerating the melting even further. This created a rapid feedback. Warming increased CO2 intensified warming, and intensified warming obliterated ice at astonishing rates, which then drove sea levels upward in giant pulses. These feedbacks were crucial for Earth's rhythm, because they magnified small orbital changes into massive global climate responses, transforming a slight tilt in Earth's axis into a worldwide surge of meltwater. The coastal world during these warm peaks was radically different from the cold stages. Ocean temperatures rose, coral reefs flourished, mangroves expanded into new territories, and warm water species migrated into regions that had been frigid just a few thousand years earlier. Beaches that had once been far out on continental shelves now lay deep underwater, and as the ocean rose, it flooded river valleys, creating long estuaries where sediment accumulated in layers that modern geologists now analyze to reconstruct these ancient transitions. The suddenness of the flooding is preserved in features such as drowned forests, tree stumps still rooted in ancient soil but now submerged beneath many meters of seawater, silent records of a time when sea level outpaced the lifespan of a coastline. One remarkable consequence of these interglacial floods is that they helped shape the world's modern underwater landscapes. Many continental shelves have terraces, flat, step-like surfaces that formed when sea levels paused temporarily during a warm peak before rising again. These terraces act like historical fingerprints, each one marking a moment when melting slowed just long enough to stabilize the shoreline before the next pulse of water lifted the sea higher. In regions like the Bahamas, New Guinea, and the Mediterranean, these terraces form submerged staircases that trace the rise of water during ancient warm cycles, capturing the story of Earth's shifting climate with extraordinary clarity. The speed of some of these sea level surges has stunned scientists. Although most interglacial rises took place over thousands of years, certain melt pulses, driven by rapid ice collapse, produced jumps of several meters in just centuries or even decades. These events are recorded as abrupt shifts in sediment character and sudden changes in the distribution of marine species. The warm peaks did not simply bring gentle warming, they often delivered chaos, transforming coastlines at rates fast enough to challenge even the most adaptable ecosystems. The contrast between cold and warm periods also reshaped ocean currents. During cold phases, expanding ice sheets altered wind patterns, pushing cold, salty water deeper into the ocean and strengthening the thermohaline circulation. But during warm peaks, meltwater freshened the surface, disrupted circulation, and sometimes triggered feedbacks that altered climate far beyond the poles. These circulation shifts influenced tropical rainfall patterns, monsoon behavior, and the distribution of nutrients in the seas, meaning that the sea level pulses were not merely vertical movements, they were whole system reorganizations with consequences that rippled across the globe. And through all of this, the underlying cause remained simple yet profound. Ice sheets grow slowly and melt quickly because accumulation requires thousands of winters, but collapse requires only a few summers strong enough to push the system past its tipping point. This imbalance created the dramatic asymmetry in sea level pulses, slow descents into glacial lows and rapid surges into interglacial highs, turning Earth's climate into something like a slow, heavy pendulum lifted carefully upward by cold and then dropped suddenly by heat. It is this rhythm that gave the oceans their giant pulses, and it is this rhythm we continue to trace through the last 3 million years. These warm peaks, though brief, were transformative. They carved the blueprint for later, more extreme flooding events. They demonstrated how sensitive ice sheets were to small climate changes, and they produced some of the earliest large-scale sea level rises that would one day influence human migration routes. The world was not yet ready for the super ice sheets that would come later, nor for the monumental 100,000-year cycles that would dominate the last million years. But it was already learning how to breathe in water and breathe it back out again, setting the rhythm that would define the rest of Earth's Pleistocene story. Orbital rhythms take control, not gently, not subtly, but with a precision so steady that once scientists finally decoded the pattern, it felt as though Earth itself had been keeping time to an ancient celestial metronome for millions of years. And as we drift deeper into the early Pleistocene, the rise and fall of sea levels begins to synchronize with those astronomical cycles so closely that the oceans might as well have been reading the sky. These rhythms, known as Milankovitch cycles, were governed by 3 movements: eccentricity, a 100,000-year stretching of Earth's orbit; axial tilt, a 41,000-year rocking of Earth's angle; and precession, a 23,000-year wobble of Earth's orientation toward the Sun. Each of these cycles altered the distribution of sunlight across the planet, especially at high latitudes, and the northern ice sheets, already sensitive, already unstable, responded to even the smallest shifts, pulling sea levels downward or releasing meltwater upward in vast pulses that matched the cosmic dance overhead. During this period, the most dominant rhythm was still the 40,000-year obliquity cycle. Earth's axial tilt shifted between about 22 and 24.5 degrees, and every time the tilt decreased, summers in the northern latitudes grew milder, allowing snow to survive, ice to accumulate, and sea levels to fall. When the tilt increased again, summers became stronger, melting the vulnerable northern ice and flooding the oceans in great surges. These swings were not minor. They often shifted global sea levels by tens of meters, and the geological record shows an exquisite harmony between these orbital changes and the planet's frozen and liquid responses. Marine isotope data, coral terraces, and coastal sediments all track this timing with astonishing precision. Every low in sunlight corresponds to low sea level. Every high in sunlight corresponds to a rapid rise. The beauty of these orbital controls is that they reveal the planet's sensitivity to solar energy. Because the actual change in sunlight delivered by Milankovitch cycles is quite small, just a few watts per square meter, yet the climate responds with massive reorganizations, and nowhere is this more clearly recorded than in sea level. The northern ice sheets grew during periods when summer sunlight weakened, locking away as much as 50 to 70 meters of sea level equivalent. And when summer sunlight strengthened again, the ice collapsed in giant waves that stored water to the oceans. These repeated cycles built the early Pleistocene pattern into something recognizable. A rise and fall, rising as fast as melting could allow and falling as slow as accumulation required, all timed to the celestial rhythms that choreographed Earth's climate from the background. One remarkable aspect of these orbital rhythms is how they interacted with Earth's geography. The northern hemisphere contains far more landmass than the southern hemisphere, meaning any change in solar energy at northern latitudes affected ice growth disproportionately, because land allows snow to accumulate in ways that open ocean cannot. Antarctica already held a vast portion of Earth's ice, but it was relatively stable. The real action, the real movement, happened in the north, where orbital forcing could grow or destroy ice sheets that directly translated into enormous sea level changes. This asymmetry explains why the Pleistocene cycles became so dramatic once northern glaciation began. The configuration of continents essentially magnified the influence of orbital rhythms, turning small cosmic nudges into global climate reorganizations. Precession also played a role, shifting the timing of seasons relative to Earth's position around the Sun. When the northern hemisphere summer occurred far from the Sun due to precession, summer energy weakened, favoring ice growth and lowering sea level. When northern summer coincided with perihelion, the point where Earth is closest to the Sun, melting intensified, accelerating sea level rise. These precessional cycles, overlapping with axial tilt cycles, created complex patterns in the sea level record, but despite the complexity, the rhythm remained unmistakably orbital. Sediment layers on ocean floors contain alternating bands of coarse and fine material, each layer marking a glacial or interglacial moment and each perfectly aligning with predicted cycles of sunlight. The eccentricity cycle, 100,000 years stretching and squeezing of Earth's orbit, was still a minor player during this early stage, but it influenced the strength of precession, modulating how dramatically seasons could warm or cool. Even though eccentricity did not directly control ice sheets yet, its influence grew slowly, setting the stage for the massive shift that would come later, the mid-Pleistocene transition. But for now, the 41,000-year tilt cycle dominated, carving the earliest deep cycles into the sea level record and providing the pacing mechanism for the young glacial world. Orbital rhythms did more than move sea level. They shaped ecosystems, climates, and future human landscapes. Every time sea levels fell, land bridges emerged, between Siberia and Alaska, between Southeast Asia and the Indonesian islands, between Britain and mainland Europe. When sea levels rose, these bridges drowned again, isolating species and shaping evolutionary paths that would one day influence early humans and the animals they depended on. Although humans were not yet on the stage, the geography that would determine their destiny was already being sculpted by the celestial heartbeat that tugged on Earth's ice and water. The orbital cycles also influenced atmospheric circulation. During glacial periods, as sea levels fell and ice sheets expanded, wind patterns shifted, deserts grew, and dust from dry continental interiors spread across oceans, providing iron that fertilized phytoplankton blooms. These blooms drew down CO2, deepening the glacial cold and reinforcing the sea level low. During warm periods, melting ice freshened the oceans, disrupted circulation, and caused CO2 to rise again, amplifying the interglacial warmth and accelerating sea level rise. In this way, orbital rhythms did not act alone. They were amplified by biological and chemical feedbacks that made their effects far larger than the initial solar variations. The precision of these cycles is what allows modern scientists to reconstruct ancient sea levels with such confidence. Each warm peak, each cold trough, each glacial advance and retreat corresponds to a predictable configuration of Earth, Sun, and orbit. And because the record aligns so perfectly, we can trace every major pulse of the last 3 million years like chapters in a long, slow-turning book. The sea level pulses did not happen randomly. They were locked to the sky, responding faithfully to the slow turning of cosmic wheels far above. By allowing orbital rhythms to take control, Earth entered a new climatic regime, one where ice sheets would grow and collapse with regularity, where sea levels would swing wildly between high stands and low stands, and where the very shape of continents would change repeatedly over the coming millions of years. This was the foundation on which the next great transformation would occur. The amplification of these cycles, the deepening of the glacial oscillations, and the eventual shift that would elevate the 100,000-year cycle into dominance. But before that turning point arrived, Earth spent nearly 2 million years breathing gently in 41,000-year pulses, letting the celestial engine tune the oceans and preparing the climate system for the next escalation in its long, rhythmic story. The 41,000-year pulse era settled over Earth like a long, measured breath, a rhythm so steady that for nearly 2 million years the planet rose and fell in a repeating pattern of ice growth and ice retreat. And during this time, sea levels responded with elegant regularity, dropping slowly as northern ice sheets expanded and then surging upward as they melted, creating a world where coastlines shifted in predictable sweeps that matched the sway of Earth's axial tilt. This era, spanning roughly from 3 million to about 2 million years ago, was defined by the dominance of the obliquity cycle, the gentle rocking of Earth's tilt between 22 and 24.5 degrees, and each shift in that angle dictated how strongly northern summers warmed, which in turn determined whether ice accumulated or vanished. The sea level record from this time reads like a soft, undulating waveform, gradual descents of 40 to 60 meters into glacial lows, followed by swift rises back toward warm interglacial highs, all paced by the same 41,000-year rhythm as if the oceans were following a script written across the heavens. During this era, the ice sheets were significant, but not yet monstrous. They expanded across northern Canada, Greenland, Scandinavia, and parts of Siberia, but they did not yet stretch all the way into the mid-latitudes in massive continental domes like they would later. Because of that, the sea level amplitude, though dramatic, was still moderate compared to the colossal swings of the later Pleistocene. Yet, even a 50-meter rise or fall was enough to redraw coastlines completely. When sea levels dropped, vast continental shelves were exposed, turning shallow seas into forests, grasslands, and river valleys. When sea levels rose, those same landscapes drowned beneath warm, shallow waters in which corals flourished. This cycle repeated again and again, giving rise to alternating layers of marine and terrestrial sediments along the world's coasts, natural archives of Earth's climate heartbeat. The beauty of the 41,000-year era is its consistency. Every time the tilt decreased and high-latitude summers cooled, the ice expanded, a slow process requiring tens of thousands of winters, with each season adding only a thin snow layer that compacted gradually into ice. As the ice thickened, sea levels declined in a slow, deliberate drop that took many millennia. But when the tilt peaked and high-latitude summers grew strong again, the system flipped almost suddenly. The accumulated ice became unsustainable, meltwater raced across glacial surfaces, subglacial lakes drained catastrophically, and within just a few thousand years, the sea surged upward, sometimes rising 10 to 20 meters per millennium. These sharp interglacial rises created high-stand beaches and coral terraces that now sit perched above modern sea level, their elevations recording the timing of each warming pulse. The moderate but steady pulses of this era also shaped global ecosystems profoundly. During glacial lows, exposed lands connected continents. The Bering Land Bridge between Siberia and Alaska emerged repeatedly, though no humans yet existed to cross it. Sunda and Sahul, the great landmass connecting Southeast Asia and Australia, expanded into vast plains. Britain fused with Europe, and countless islands became peninsulas. These land bridges allowed animals to migrate freely. Mammoths, giant deer, early horses, predators, and countless smaller species moved across continents in ways that would be impossible today. When sea level rose again, these corridors drowned, isolating populations on islands and driving evolutionary changes that later produced unique species, from dwarf elephants on Mediterranean islands to distinct lineages of rodent, bird, and reptile species. One of the most important aspects of the 40,000-year era is how well the geological record captures its rhythm. Oxygen isotope cycles in deep-sea sediments show clean, smooth oscillations matching the tilt cycle almost perfectly. Coral terraces in places like Tahiti, Barbados, and the Huon Peninsula reveal sequences of high stands separated by consistent time intervals. Loess, wind-blown dust deposits, also records this rhythm. Thicker layers correspond to colder, drier glacial times when sea levels were low, while soil layers reflect warm interglacials when vegetation stabilized landscapes. These independent records reinforce the same conclusion. During the earliest Pleistocene, Earth's sea levels moved in lockstep with axial tilt. And yet beneath this stability lay the seeds of change. The ice sheets were growing, not just as large patches, but as interconnected systems capable of storing more and more water. Each cycle added slightly more ice than the previous one in some regions, gradually increasing the planet's sensitivity to climate shifts. Over time, the Laurentide and Fennoscandian ice sheets began to interact more strongly with atmospheric circulation, reshaping wind patterns and enhancing cooling in ways that subtly altered the climate engine itself. Ice sheets became taller, colder, and more deeply entrenched, which increased their inertia, meaning it took more energy to melt them, but once melting began, the collapse was far more catastrophic. During warm intervals, global temperatures hovered only 1 to 2 degrees above modern levels, yet those small increases were enough to remove vast masses of ice. Sea levels during some interglacials stood 10 to 25 meters higher than today, submerging what are now major coastal plains. The Red Sea narrowed and widened repeatedly. The Persian Gulf filled and emptied, and the coastline of North America shifted hundreds of kilometers over the cycles. These changes influenced ocean salinity, circulation patterns, nutrient availability, and even the development of coral reef ecosystems, which expanded dramatically during warm periods, only to suffer die-offs when sea levels fell and water temperatures shifted. This era is also important for what it reveals about greenhouse gas behavior. The 41,000-year pulses are tightly tied to CO2 fluctuations. During glacial periods, CO2 levels dropped as cold oceans absorbed the gas. During interglacials, CO2 rose again as temperatures warmed and deep ocean reservoirs released stored carbon. These CO2 changes amplified the orbital cycles. Small changes in sunlight produced large changes in climate because the carbon cycle acted as a multiplier. Each interglacial warming was thus sharper, each sea level rise faster than orbital forcing alone could explain. This amplification mechanism remains one of the most important insights for understanding both past and future sea level behavior. The long stability of this era ended not because something broke, but because something crossed a threshold. Ice sheets eventually grew large enough, thick enough, and cold enough to behave differently. Their increased mass altered the crust beneath them, depressed continents, rerouted rivers, and changed precipitation patterns. They became capable of sustaining deep glacial phases, lasting far longer than 41,000 years. And once this threshold was crossed, the climate no longer responded primarily to tilt. It shifted into a new mode dominated by longer cycles, deeper glaciations, and far more dramatic sea level swings. But before that great transition, Earth spent millions of years in this relatively gentle rhythm, inhaling and exhaling water in 41,000-year pulses, reshaping coastlines, sculpting ecosystems, and setting the stage for the more violent oscillations that would follow. This era was the overture, the slow opening movement of a symphony that was about to grow far louder, far deeper, and far more dramatic as the ice sheets reached their next evolutionary step. The ice threshold phenomenon emerged quietly at first, almost invisibly, yet it marked one of the most important turning points in Earth's climate history, because as the northern ice sheets thickened and spread during the long 41,000-year pulse era, they eventually crossed a series of physical thresholds, tipping points, that transformed their behavior from gentle, predictable growth and retreat into something far more dramatic. Sudden collapses, runaway melting, and sea level surges far larger and sharper than anything seen in earlier cycles. The key to this shift lies in how ice behaves when it becomes extremely massive, because beyond a certain size, the geometry, temperature structure, and internal dynamics of an ice sheet change completely, making it vulnerable to abrupt disintegration even when the warming pushing it is modest. As the Laurentide and Eurasian ice sheets expanded toward their mid-Pleistocene configurations, their base sank into bedrock below sea level, their thickness exceeded 2 kilometers in some regions, and they began storing not just tens of meters of sea level equivalent, but more than 100, creating the conditions for collapses far more catastrophic than anything the planet had experienced up to this point. At its core, this threshold phenomenon is simple. Small ice sheets melt gradually, large ice sheets melt catastrophically. Once they surpass certain limits of thickness, height, and grounding depth, ice sheets lose stability. The bottom layers warm from pressure, meltwater accumulates beneath them, sliding becomes easier, and the entire sheet becomes capable of retreating rapidly when triggered by even slight increases in summer sunlight. In earlier eras, the northern ice sheets were too small to behave this way. They expanded and melted in smooth, almost elegant responses to orbital forcing. But as they grew thicker in the late 41,000-year cycle era, around 1.5 to 1.2 million years ago, they crossed into a new regime where the energy needed to destabilize them became much smaller than the energy needed to build them, creating a climate system primed for abrupt terminations of glacial periods. Evidence for this shift appears in marine sediment cores, which begin showing more dramatic ice-rafted debris layers, coarse materials dropped into the ocean by melting icebergs, indicating ice sheets were breaking apart in larger pieces and retreating more violently than before. These layers grow thicker and more frequent as Earth approaches the mid-Pleistocene transition, marking a world where melt events were no longer steady declines but explosive collapses. The sea level record mirrors this shift with increasing amplitude. Instead of rises of 30-50 meters at the end of glacial periods, the planet begins experiencing rises of 60-80 meters, and later even more than 100 meters, all in relatively short geological windows. The oceans responded instantly to these collapses, surging upward in pulses that drowned entire continental shelves, erased coastlines that had existed for tens of thousands of years, and forced ecosystems to reorganize with each new flood. One of the key mechanisms behind these sudden collapses is marine ice sheet instability. As the ice sheets grew, their grounding lines, the points where ice transitions from resting on land to floating on seawater, moved onto bedrock that sloped downward inland. This inverted topography meant that once warm water penetrated beneath the ice, the grounding line could retreat rapidly into deeper and deeper basins, accelerating the melting in a runaway feedback. This process is well documented in modern West Antarctica, but during the early Pleistocene, it began to appear first in the growing northern ice sheets. Although not all northern ice rested on marine basins, enough sectors did that their destabilization became a powerful driver of rapid sea level changes. Once triggered, these collapses were effectively unstoppable until the ice had retreated to a point of stability far inland. Another crucial threshold involved albedo feedback. As ice sheets grew beyond a certain size, they reflected more solar radiation, cooling the climate and promoting even more ice accumulation. But the reverse was also true. Once melting began and dark surfaces, rock, water, soil, emerged, solar absorption increased dramatically, accelerating the collapse. Large ice sheets are therefore inherently more unstable near their melting point than smaller ones. During warming intervals, the loss of even a few % of surface area could destabilize the entire structure, causing meltwater rivers to cut channels through the ice, lakes to burst from within, and huge sectors to break away and melt in the ocean. This shift from gradual to catastrophic melting profoundly changed Earth's sea level rhythm. Instead of gentle interglacial rises, the world began to see sharp pulses, abrupt, steep jumps marking the violent termination of glacial periods. These pulses not only drowned coastlines, but also affected global climate systems. When massive meltwater floods poured into the oceans, they disrupted thermohaline circulation, altering heat transport across the planet. In some cases, these disruptions caused temporary cooling episodes, even during overall warming trends, creating complex climate feedbacks that shaped vegetation patterns, migration routes, and the structure of marine ecosystems. Sediment cores from the Red Sea, which preserve one of the most accurate continuous sea level records, show that around 1.2 million years ago, the amplitude of sea level changes began increasing significantly. Instead of oscillating primarily within a 60-meter range, the planet started swinging between lows more than 120 meters below modern sea level and highs approaching or exceeding modern levels. This doubling of amplitude marks the moment when the ice sheets had grown large enough to behave like the massive, unstable giants that would later dominate the 100,000-year cycle era. The Red Sea record also shows that the pace of sea level rise during melt pulses increased, with some transitions occurring in as little as 8,000 to 10,000 years, a geological instant for such monumental changes. As the ice sheets crossed these thresholds, they reshaped global landscapes dramatically. During glacial maxima, sea levels dropped so far that continental shelves were exposed worldwide. The English Channel became a grassy valley. Java and Sumatra connected to mainland Asia, Australia, and New Guinea formed a single continent, and the Persian Gulf existed as a vast desert plain watered by ancient river systems. But when the ice sheets collapsed at the end of these glacial phases, these same regions were inundated rapidly. Coastlines leapt inland by tens of kilometers, valleys filled with seawater, and ecosystems were forced either to migrate uphill or vanish beneath the rising tides. These drowned landscapes, submerged forests, ancient riverbeds, stone tools lying offshore, remain preserved beneath coastal waters today, silent witnesses to the abruptness of these threshold-driven sea level jumps. This threshold phenomenon also explains why glacial cycles began to lengthen and deepen. Once ice sheets grew large enough to be hard to melt entirely in a single obliquity cycle, some glaciations began skipping warm peaks, persisting into the next tilt cycle and accumulating even more mass. This allowed ice sheets to survive longer cold periods and reach sizes unheard of in earlier epochs. The climate system, once governed smoothly by the 40-once-a-year cycle, started drifting toward a new mode dominated by deeper, longer cycles with more violent endings. This slow drift set the stage for the mid-Pleistocene transition, the moment when Earth's climate rhythm shifted into the powerful 100,000-year pattern that would dominate the rest of the Pleistocene. Thus, the ice threshold phenomenon was not a single event, but a quiet revolution in Earth's climate machinery, a shift from gentle pulses to deep throbs, from modest ice sheets to towering frozen continents, and from slow sea level movements to explosive surges. And once these thresholds were crossed, Earth's heartbeat would never be the same. CO2 feedback loops were the hidden amplifiers behind every major rise and fall in sea level across the last 3 million years. And while orbital rhythms set the timing and ice thresholds set the scale, it was carbon dioxide that determined just how intensely the planet warmed or cooled during each cycle, shaping the size of melt pulses, the depth of glacial lows, and the violence of each transition between them. The remarkable thing about CO2 is that it rarely acts alone. It responds to changes in ocean temperature, vegetation shifts, dust levels, and biological productivity. Yet in responding, it also feeds back into the system, amplifying the very changes that triggered it. In a climate machinery already growing more sensitive due to expanding northern ice sheets, CO2 became the lever that could swing sea levels upward or downward with accelerating force, turning modest orbital nudges into climate events powerful enough to redraw the continents over and over again. During glacial periods when sea levels fell and vast ice sheets spread across the northern world, the oceans absorbed more carbon dioxide. Cold water holds more CO2, and as surface temperatures dropped, the upper layers of the ocean pulled carbon from the atmosphere, lowering global concentrations. At the same time, strengthened winds and increased dust deposition, fueled by exposed continental shelves and expanding deserts, fertilized the ocean with iron, stimulating massive phytoplankton growth. These microscopic organisms drew even more CO2 from the air, incorporated it into their shells, and carried it to the deep ocean when they died. As a result, atmospheric CO2 during glacial lows often dropped to around 180-200 ppm, much lower than modern pre-industrial levels, intensifying the cold and allowing ice sheets to grow more massive than they could through orbital forcing alone. When the climate began to warm at the end of a glacial cycle, this entire system reversed itself with astonishing speed. As sunlight increased due to orbital shifts, the oceans began to release CO2 rather than absorb it. Cold, deep waters upwelled, bringing carbon-rich water to the surface where the gas escaped into the atmosphere. Melting ice sheets weakened winds and reduced dust supply, slowing phytoplankton blooms and decreasing biological carbon storage. Vegetation expanded across newly warmed continents, soils thawed, and methane from ancient reservoirs seeped into the atmosphere. All of these processes added greenhouse gases to the air, strengthening the warming pulse. And as temperatures rose, the oceans released even more CO2, enhancing the feedback further. This amplification had a profound effect on sea levels. Orbital forcing alone might have melted part of an ice sheet, but with CO2 feedback, the melting intensified until entire sectors collapsed. The result was sea level rise not of a few meters, but of tens of meters, delivered in pulses far too fast to be explained solely by sunlight variations. CO2 essentially turned slow warming into rapid warming, and rapid warming into ice sheet failure. Warm interglacials, such as marine isotope stage 11, around 400,000 years ago, and stage 5e, around 125,000 years ago, were not just mild interludes. They were times when global temperatures rose high enough, for long enough, to melt ice sheets extensively. And in each case, CO2 reached peak concentrations that magnified the sea level response dramatically. But even before those later interglacials, during the earlier Pleistocene, CO2 feedbacks were already shaping sea level pulses. Around 2.5 million years ago, CO2 levels began trending downward as Earth cooled overall, making the climate increasingly responsive to orbital changes. When tilt decreased, temperatures fell sharply, ice accumulated rapidly, and sea levels plummeted because low CO2 locked in the cold. When tilt increased again, CO2 levels rose, enhancing the melt and driving sea levels upward with increasing intensity. Over time, the amplitude of these changes grew, because each new glaciation stored more CO2 in the deep ocean and in frozen soils, making each subsequent deglaciation even more dramatic once warming began. One of the most critical aspects of CO2 feedback is how it interacts with ocean circulation. The global conveyor belt, the thermohaline circulation, plays a major role in determining how much carbon stays in the deep ocean versus how much reaches the surface. During glacial periods, strong circulation pulled CO2 into the deep ocean, locking it away. But during deglaciations, meltwater from collapsing ice sheets disrupted circulation patterns, slowing the sinking of cold, salty water in the North Atlantic and altering the entire balance of CO2 storage. These disruptions caused periodic bursts of CO2 into the atmosphere, which correspond closely with sharp warming spikes and rapid sea level jumps recorded in coral terraces and sediment cores. The link is clear. Each major jump in CO2 aligns with a major pulse of sea level rise. Dust also played a pivotal role in these feedback loops. During the coldest phases of glaciation, deserts expanded and winds strengthened, delivering enormous quantities of iron-rich dust into the oceans. This fertilization stimulated photosynthetic productivity, drawing down massive amounts of CO2 and making glacial periods even colder. But when melting began, dust levels collapsed almost overnight as landscapes grew wetter and vegetation returned. Without dust, phytoplankton blooms diminished, CO2 removal slowed, and atmospheric concentrations climbed rapidly, helping to trigger the abrupt end of glacial periods. These dust-driven feedbacks make the difference between a gentle melting and a catastrophic meltdown. The CO2 record preserved in Antarctic ice cores reveals these loops in exquisite detail. Every glacial period shows a slow decline in CO2, followed by a rapid ascent, and every major interglacial warming aligns with a spike in CO2. Meanwhile, sea level records show the same pattern: slow descent, rapid rise. CO2 acts as both signal and driver, both indicator and amplifier. The oceans mark its rise and fall with shorelines that shift hundreds of kilometers over each cycle. These CO2 loops also determined the landscape that early humans would one day traverse. When CO2 was low, sea levels dropped dramatically, exposing land bridges and expanding migration routes. When CO2 rose, coastlines drowned, populations were isolated, and genetic lineages split. Even though humans do not appear until much later in this story, the corridors that shaped their dispersal were carved by these ancient atmospheric rhythms. Most importantly, CO2 feedback loops prepared the climate system for the mid-Pleistocene transition. As ice sheets grew larger and thicker over successive cycles, they stored increasingly massive amounts of CO2 in ocean reservoirs and frozen soils. Each new glaciation lowered CO2 farther, making the next glaciation colder, longer, and more intense. Over time, glacial cycles became too large to melt fully every 41,000 years, and the system began skipping warm peaks entirely, a change that ultimately gave rise to the new, more powerful 100,000-year rhythm. Thus, CO2 feedback loops were not just climate details. They were the hidden engine behind the amplification of sea level pulses, the deepening of glacial cycles, and the transformation of Earth's climate into the dramatic, unstable, breathtakingly dynamic system that would dominate the last million years. Ocean conveyor instability was the silent architect behind some of the fastest, most dramatic sea level swings of the last 3 million years. Because while ice sheets controlled the amount of water locked on land and CO2 determined the strength of warming, it was the global circulation of the oceans, the great thermohaline conveyor, that determined how quickly that water melted, where heat accumulated, how storms shifted, and whether the planet moved gently or violently between glacial lows and interglacial highs. The conveyor is powered by the sinking of cold, salty water in the North Atlantic, which pulls warm water from the tropics northward, releases heat into the atmosphere, and then drives a deep return flow that circles the world. But the moment that sinking weakens or stops, the entire system reorganizes. And when this happened in the Pleistocene, it often caused sea levels to rise far faster than orbital forcing alone could explain, because heat piled up in certain parts of the ocean, destabilizing ice sheets from below and accelerating their collapse. To understand how this instability shaped sea level pulses, imagine what happens when massive meltwater floods, released from collapsing ice sheets during warming phases, pour into the North Atlantic. Fresh water is less dense than salty seawater, so these floods capped the ocean with a buoyant layer that prevented cold water from sinking. With the conveyor weakened or stalled, heat that would normally be transported northward became trapped in the southern hemisphere and the tropics, warming ocean surfaces and undermining the edges of marine terminating ice sheets in West Antarctica and parts of Greenland. This redistribution of heat did not raise sea levels directly by adding water. It raised sea levels indirectly by melting ice more quickly and causing grounding lines to retreat at speeds that shocked even experienced paleoclimatologists. Sediment cores from the mid-Pleistocene show layers of ice-rafted debris that correspond to conveyor slowdowns, meaning each time the circulation faltered, ice sheets disintegrated more violently. The conveyor also shaped sea level falls. During glacial periods, as sea levels dropped and coastlines expanded outward, new wind patterns intensified the production of dense, salty water in the North Atlantic. Stronger sinking accelerated the conveyor, pulling even more heat from high latitudes and stabilizing cold conditions, which allowed ice sheets to grow further and sea levels to fall more deeply. Dust blowing into the oceans fertilized phytoplankton blooms, which removed CO2 and cooled the climate even more, strengthening the conveyor's grip. But such stability always carried the seeds of its own disruption. Once the ice sheets grew large enough to destabilize, their eventual melt pulses would again release torrents of fresh water that broke the conveyor's rhythm, producing abrupt warming events in some regions and abrupt cooling in others, chaos that translated into rapid sea level movements. One of the clearest examples of conveyor instability occurred around 1.5 million years ago, during a period of increasing glacial depth and rising sea level amplitude. Marine isotope records show that several glaciations ended with unusually steep melt pulses, indicating that ice sheets collapsed in sudden bursts rather than slow retreats. At the same time, ocean cores from the North Atlantic reveal unusually fresh surface waters, evidence of massive meltwater flooding and a collapse of deep water formation. When the conveyor shut down, warm water accumulated along continental margins, weakening ice shelves from below and accelerating grounding line retreat. The result was sea level rise that unfolded far faster than the orbital shift alone could produce, marking conveyor instability as one of the dominant amplifiers of Pleistocene sea level behavior. These disruptions also affected climate patterns across Africa, Asia, and the Americas. When the conveyor weakened, the intertropical convergence zone shifted southward, monsoon systems weakened or collapsed, and vast regions experienced drought. These changes altered vegetation patterns, dust production, and CO2 uptake, each of which fed back into the global climate system, further amplifying the very warming that had triggered the conveyor's collapse. Sea level responded to this chain reaction in a predictable but powerful way. The more disrupted the conveyor, the more heat accumulated beneath ice shelves, and the faster the melt occurred. In places like the Labrador Sea, temperature spikes of 3 to 5 degrees at depth during conveyor slowdowns are recorded in microfossil assemblages, warming sufficient to destabilize massive glacial outlets. The conveyor's role in the giant pulses becomes even clearer when examining meltwater pulse events, brief intervals when sea level rose several meters in just centuries. Although the most famous of these occurred later, near the end of the last ice age, similar but smaller pulses appeared repeatedly across the mid-Pleistocene. Each one corresponds to a reorganization of the conveyor. When the conveyor slowed, warm water accumulated in subsurface layers. When it recovered, that warm water was transported northward and upward, destabilizing ice sheets suddenly. These hot-cold switches forced sea level curves into sharp spikes instead of smooth transitions. In effect, the conveyor acted like a switchboard that controlled where the planet stored its heat, and whenever the wiring changed, sea level changed with it. This instability also shaped evolutionary landscapes long before humans appeared. When the conveyor strengthened during deep glaciations, cold, dry conditions spread across continents, lowering sea levels and creating new migration corridors for megafauna. When the conveyor weakened abruptly, coastlines drowned, islands formed, and populations became isolated. These geographic reorganizations influenced species ranges, extinction patterns, and evolutionary bottlenecks. Later, when early humans emerged, their migrations into Eurasia and across coastal regions would depend heavily on the sea level landscapes carved by conveyor-driven climate shifts. The Pleistocene Ocean was not just a passive reservoir receiving meltwater. It was an active agent in determining how quickly ice melted and how high seas rose. The conveyor's periodic breakdowns acted like accelerators on the climate engine. By the time the world approached the mid-Pleistocene transition, conveyor instability had become a recurring feature of glacial terminations, helping to push ice sheets past their structural thresholds and producing the explosive deglaciations that define the later Pleistocene. The system had entered a mode where sea level pulses no longer rose and fell gently. They lurched, they surged, they dropped off cliffs, responding to intricate interactions between ice, atmosphere, and deep ocean currents. Conveyor instability also played an important role in why glacial cycles eventually lengthened. As ice sheets grew larger, the effects of meltwater flooding became more dramatic, disrupting the conveyor for longer periods and creating extended cold recoveries afterward. These prolonged disruptions allowed ice sheets to survive through multiple orbital warm peaks, accumulating more mass and deepening the next glaciation. Sea levels during these extended glacial periods dropped farther than ever before, sometimes more than 120 meters below modern levels, exposing continental shelves on a scale that reshaped entire continents. Those lost shorelines still lie beneath the ocean today, preserved in sonar maps as ancient river systems cut into what is now the seabed. By controlling where heat went, where it stayed, and when it moved, the conveyor determined not only the pace of melting, but also the stability of ice sheets themselves. It took relatively little to push the conveyor off balance: a few thousand cubic kilometers of meltwater, a shift in storm tracks, or a slight change in ice edge geometry. But once it tipped, the consequences were global, and sea level responded powerfully. Conveyor instability transformed the climate into a more chaotic, pulse-driven system, preparing the stage for the full transition to 100,000-year cycles, cycles marked not by gentle oscillations, but by deep freezes, violent thaws, and sea level jumps large enough to carve the coastlines of the world into the shapes we recognize today. The mid-Pleistocene transition, often called the MPT, was one of the most dramatic turning points in Earth's climate history, a shift that transformed the planet's rhythm from gentle 41,000-year ice pulses into the deep, brutal 100,000-year cycles that would dominate the last million years. And with this shift came sea level swings far larger, slower, and more violent than anything the earlier Pleistocene had ever produced. Occurring roughly between 2 million and 900,000 years ago, the MPT was not a single event, but a long, uneven transformation in which the climate system gradually reorganized itself, driven by growing ice sheets, falling CO2, and increasingly unstable ocean circulation, until the old pattern finally broke and a new one took its place. Before the MPT, sea levels oscillated by perhaps 50 to 60 meters in response to tilt-driven glacial cycles. After the MPT, they plunged more than 120 meters during deep glaciations and surged back to near-modern levels in violent melt pulses, creating the enormous sea level amplitude that characterizes the late Pleistocene. To understand why the MPT occurred, we must look at the gradual changes that had been building for hundreds of thousands of years. First, northern ice sheets were growing larger with each successive cycle. Subtle long-term cooling and strengthened glacial feedbacks allowed ice to accumulate to greater thicknesses, and as these sheets expanded, they crossed the critical thresholds described earlier. Their bases sank deeper into over-deepened basins, their grounding lines moved across reverse-sloping bedrock, and their internal temperatures dropped low enough for colder, more brittle ice to dominate. These changes made the ice sheets harder to melt fully in a single 41,000-year warm peak. As a result, some glacial cycles began skipping interglacials altogether, remaining frozen through the warm phases and continuing to accumulate mass into the next cycle. This allowed glaciations to extend for 80,000, 100,000, or even 120,000 years, far longer than the earlier pattern. Second, atmospheric CO2 continued a slow, long-term decline through the early Pleistocene, reducing global temperatures and increasing the sensitivity of ice sheets to orbital changes. Lower CO2 meant colder oceans, stronger dust cycles, and deeper glaciations, all of which pushed ice sheets to sizes that fundamentally altered their behavior. This declining CO2 trend, observed in benthic foraminifera and ice cores, did not cause the MPT by itself, but it primed the climate system for a regime shift by lowering the baseline temperature enough that glacial cycles could begin stacking, merging, and deepening in a way that had never happened before. Third, ocean conveyor instability became more pronounced as ice sheets grew massive. The meltwater floods that accompanied early deglaciations disrupted the Atlantic meridional overturning circulation more severely, and the lingering effects of these breakdowns caused repeated cooling rebounds that prevented complete melting. In some cycles, a meltwater pulse shut down the conveyor entirely, plunging the climate back into cold conditions even as orbital forcing favored warmth. With the conveyor weakened or unstable, the Earth occasionally found itself unable to exit a glaciation properly, trapping the planet in prolonged cold phases that allowed ice sheets to grow to unprecedented sizes. All of these processes converged around 1.2 million years ago, when the first signs of the MPT appear in the marine isotope record. Instead of smooth 41,000-year oscillations, the climate curve begins to show longer, deeper freezes, followed by sharper, more explosive terminations. Sea level reflected this fundamentally new behavior. During glacial lows, sea levels fell farther than ever before, sometimes more than 90 meters below modern levels even before the MPT fully matured. During terminations, when warming finally overcame the ice thresholds and CO2 feedbacks accelerated the collapse, the resulting rise in sea level occurred so fast and so massively that entire continental shelves vanished beneath the water in a geological instant. The MPT also transformed the shape of coastlines permanently. Regions like the Bering Strait became far more frequently exposed, sometimes for tens of thousands of years at a stretch, while coastlines in Europe, Southeast Asia, and the Americas moved tens of kilometers outward during deep glacial lows. But the high stands became more intense as well. During major interglacials such as MIS 11 and MIS 5e, sea levels rose several meters above modern levels, drowning forests, carving new estuaries, and building coral terraces that still ring tropical islands today. These high stands testify not only to the strength of interglacials, but to the violence of the transitions that preceded them. One of the defining features of the MPT is the emergence of sawtooth cycles in the climate record. Slow, steady glacial buildups followed by rapid, catastrophic deglaciations. Sea level followed the same sawtooth pattern: slow, deliberate descent into glacial lows, then abrupt, steep rises that could deliver 30–40 meters of sea level increase in just a few thousand years. In some cycles, sea level rise exceeded 10 meters per millennium, a rate fast enough to drown coastal plains, submerge low-lying islands, and force entire ecosystems to migrate uphill in lockstep with the moving shoreline. Why did the cycle length shift from 41,000 to 100,000 years? The answer lies in the internal dynamics of large ice sheets. Once ice masses grew beyond a critical size, they became sensitive not just to variations in tilt, but to eccentricity-modulated precession cycles, the 100,000-year pattern. Although eccentricity itself produces very small changes in total sunlight, its influence on the timing and strength of seasons became decisive when ice sheets were enormous. Large ice sheets needed much more warming to melt fully, and precession plus eccentricity provided occasional super summers strong enough to produce full deglaciations. But these occurred only every 80,000 to 120,000 years. All other warm peaks were simply too weak to overcome the massive glacial inertia. Thus, after the MPT, sea level rise became tightly linked to unusually strong insolation peaks that occurred only when precession and eccentricity aligned favorably. These rare alignments were the triggers for full deglaciation, and every time they hit, the resulting terminations were spectacular. Global sea level surges, conveyor reorganizations, CO2 spikes, and climate transformations that reshaped ecosystems, coastlines, and evolutionary landscapes across the world. The MPT also created the glacial backdrop against which early humans evolved. Although humans did not yet play an active role in shaping coastlines, the landscapes that would later guide their migrations, land bridges, island arcs, coastal shelves, and inland corridors, were sculpted by the deepened sea level cycles of this new era. Future human ancestors, from early Homo erectus in Africa to the later species that spread across Eurasia, would find their world repeatedly reshaped by coastlines that advanced and retreated on a scale far greater than anything earlier Pliocene ecosystems had experienced. By the time the MPT fully completed roughly 900,000 years ago, the planet had entered a new climatic age defined by extremes: deeper glaciations, higher interglacial seas, sharper transitions, and ice sheets capable of storing far more water than ever before. Sea level pulses now reached amplitudes of more than 120 meters. The rhythm of the Earth had slowed, deepened, and intensified. And this new rhythm, the 100,000-year pulse, would control the shape of continents, the evolution of ecosystems, and the geography of human journeys for the rest of the Pleistocene. The rise of super ice sheets after the mid-Pleistocene transition brought Earth into its most dramatic glacial era yet, because once the Laurentide and Eurasian ice sheets expanded into truly continental-scale giants, each storing more than 100 meters of sea level equivalent, they became the primary engines behind the largest sea level collapses in Earth's 3-million-year story, shaping coastlines not with gentle curves, but with deep, staggering strokes that lowered oceans to their most extreme limits. These super ice sheets did not simply grow larger versions of their earlier selves. They evolved into new climatic forces, towering kilometers thick, spreading far into mid-latitudes, and plunging entire regions into perpetual winter. Their sheer mass depressed the crust beneath them by hundreds of meters, rerouted rivers, created enormous glacial lakes, and locked away so much water that global sea level dropped more than 120 meters during their peak expansions, exposing continental shelves the size of nations and doubling the amplitude of earlier sea level cycles. What made these super ice sheets uniquely powerful was not just their size but their internal structure. Ice becomes layered over tens of thousands of years, compacting into dense, cold blue ice at depth while retaining brittle, fractured zones near the surface. As the sheets thickened, the weight at their bases increased the flow of ice outward, pushing massive lobes into surrounding landscapes and grounding them over reverse-sloping basins, domains highly prone to runaway retreat once warming began. Beneath the ice, pressure melted water even in deep cold, creating lubricated layers that allowed entire sectors of the ice sheet to slide kilometers in a single season. The Laurentide, in particular, grew so large that it formed multiple domes, Keewatin, Labrador, and Fox ice centers, each draining into huge glacial corridors that funneled ice into the Atlantic and Arctic. When these domes collapsed, they did so not gradually but catastrophically, sending armadas of icebergs into the oceans and lifting sea level at staggering rates. The presence of these super ice sheets fundamentally altered global climate. Their bright surfaces reflected immense amounts of sunlight, amplifying glacial cooling and prolonging the ice age conditions that allowed them to reach their enormous size. They increased global wind strength, intensified dust production, and amplified CO2 drawdown, driving atmospheric carbon to some of the lowest levels of the Pleistocene, around 180 ppm at peak glaciations. These feedbacks made glacial lows colder, drier, and more expansive, pushing ice margins to latitudes as low as 40 degree N in North America and 45 degree N across northern Europe. Sea levels at these times fell so dramatically that entire continental shelves emerged as dry land. The Bering Land Bridge did not simply appear, it became a broad expanse of tundra, stretching more than 1,000 kilometers wide. Southeast Asia transformed into the supercontinent known as Sundaland. Britain fused with Europe under ice and grasslands. Australia merged with New Guinea and Tasmania into Sahul. These landscapes were not rare events. They were the dominant environments of the late Pleistocene. The collapse of super ice sheets during interglacial transitions produced some of the largest and fastest sea level rises in Earth's climate archive. Marine isotope stage 11, around 400,000 years ago, stands as a striking example. With Earth warmed by an unusually strong orbital alignment and CO2 rising to around 300 ppm, the Laurentide and Eurasian ice sheets retreated rapidly, raising global sea level to heights 6 or 13 meters above today. Coral terraces from the Bahamas, Bermuda, and the Mediterranean show these high stands clearly. Flat, wave-cut platforms now perch tens of meters above modern tide lines. Beneath them lie the signatures of violent melt pulses, chaotic breccias, reworked sediments, and sudden shifts in fossil assemblages that mark periods when sea level jumped so quickly that coastal ecosystems had no time to adapt. Another example came during MIS 5e, roughly 125,000 years ago, when the superice sheets collapsed again under strong summer insolation. Sea levels reached 609 meters above today, drowning low-lying regions that had been exposed for tens of thousands of years. Fossil corals in the Seychelles and Red Sea record abrupt increases in sea level during this period, possibly up to several meters per century during the fastest phases. These rapid rises underscore the instability of large ice sheets. Once they cross internal thresholds, melting accelerates exponentially, driven by feedbacks in albedo, ocean circulation, and atmospheric moisture. The growth of superice sheets also left an enduring imprint on global geology. During glacial maxima, thick ice carved deep valleys, created fjords, bulldozed moraines, and sculpted drumlin fields. These landforms survive today from Canada to Scandinavia as silent witnesses to the immense power of ice. Meltwater from the collapsing Laurentide created catastrophic floods, such as the ones that carved the channeled scablands in Washington state, releasing volumes of water that dwarfed modern rivers. Similar megafloods occurred across Eurasia, reshaping entire basins. Each collapse of a superice sheet produced not just sea level rise, but profound terrestrial reconfiguration. These giant ice structures also controlled atmospheric circulation on hemispheric scales. Their height, often more than 3 kilometers, acted like mountain ranges, diverting jet streams and storm tracks. During glacial maxima, the Laurentide forced polar air deep into mid-latitudes, freezing regions that today enjoy temperate climates. The altered wind patterns expanded deserts in Africa and Asia, changed monsoon strength, and intensified dust transport into the oceans, reinforcing glacial cooling. In this way, sea level and climate were inseparably linked. The larger the ice sheets grew, the lower sea level fell, and the stronger the climatic feedbacks became. Super ice sheets also influenced early human evolution and dispersal indirectly. Though Homo sapiens emerged long after the onset of the MPT, earlier hominin species, such as Homo heidelbergensis and Homo erectus, lived in landscapes repeatedly transformed by glacial expansion and collapse. When sea levels fell during deep glaciations, migration routes opened across Eurasia. When the ice retreated, coastlines flooded and populations became isolated. The repeated exposure and drowning of coastal corridors shaped the pathways of human movement long before modern humans appeared. Ultimately, the rise of super ice sheets was not merely a climatic phase, it was a transformation of the entire Earth system. Their growth created the deep asymmetric glacial cycles of the late Pleistocene. Their collapses generated the massive melt pulses that lifted sea levels by more than 100 meters, and their presence shaped the geography and climate in which humanity would eventually evolve. With their arrival, sea level change entered its grandest era, an era defined by extremes, by sudden rises and falls, and by ice sheets powerful enough to redraw the continents again and again. Catastrophic meltwater floods were among the most dramatic events of the last 3 million years, moments when the world's great ice sheets, after tens of thousands of years of slow, methodical buildup, collapsed so abruptly that sea levels jumped not in gentle curves, but in steep, staggering surges, sometimes rising several meters within mere centuries, reshaping coastlines, drowning habitats, and unleashing torrents of fresh water into the oceans that altered global climate patterns almost overnight. These melt pulses were the explosive endings to long glacial cycles, the final act of the super ice sheets birthed after the mid-Pleistocene transition, and the evidence of their violence lies not only in coral terraces and marine sediments, but also in the carved landscapes of continents that still bear the marks of floods so immense they defy imagination. The most vivid examples of these catastrophic events come from the last several glacial terminations, but their origins stretch much further back. Sediment cores reveal that even as early as 900,000 years ago, meltwater pulses began to intensify as ice sheets grew thicker, colder, and increasingly unstable. These early deglacial events produced sudden sea level rises, recorded as sharp steps in Red Sea salinity data and as rapid isotopic shifts in foraminiferous shells. But it was after the mid-Pleistocene transition that meltwater pulses became truly explosive. The Laurentide and Fennoscandian ice sheets, now massive and perched over deep basins, did not simply retreat, they disintegrated in enormous collapses that dumped fresh water into the oceans on a scale unmatched in previous cycles. The mechanisms behind these catastrophic pulses varied between regions, but several dominant processes created the template for this repeated phenomenon. One of the most important was proglacial lake outburst flooding. During glacial periods, vast meltwater lakes accumulated along the edges of ice sheets, dammed by ice rather than by rock. Lake Agassiz, Lake Missoula, Lake Baltic, and numerous others formed across North America and Eurasia. These lakes were immense. Agassiz alone at times held more water than all the modern Great Lakes combined. When ice dams weakened during deglaciation, they burst catastrophically, releasing water volumes that rivaled small oceans. These floods roared across continents, carved canyons, transported boulders the size of houses, and delivered freshwater pulses into the oceans large enough to disrupt global circulation. Sea level did not rise uniformly from these floods alone, but the cumulative effect of multiple outbursts contributed significantly to meltwater pulses. A second mechanism was marine ice sheet instability, which occurred when the grounding lines of ice sheets retreated into deep inland basins. Once warm ocean water accessed the underside of these ice shelves, retreat became self-sustaining. Vast sectors of the Antarctic and Laurentide ice sheets collapsed rapidly during such events, releasing flotillas of icebergs that melted quickly and added continuous pulses of water to the oceans. Geological records show Heinrich events, episodes during which huge numbers of icebergs broke off from the Laurentide and drifted across the North Atlantic, marking moments when ice sheet collapse accelerated melting dramatically. Although these events are best documented for the last glacial period, similar processes occurred throughout the later Pleistocene, whenever ice crossed thresholds that made retreat irreversible. The third mechanism was surface melt runaway, in which warming summers triggered widespread melt across the ice sheet surface, leading to the formation of vast networks of lakes and rivers atop the ice. When these lakes fractured through crevasses, they delivered torrents of water to the glacier base, lubricating it and causing sudden surges in ice flow. Modern Greenland experiences small versions of this phenomenon, but during the late Pleistocene, when ice sheets were far larger, these surges could accelerate retreat across entire regions. Meltwater plumbing systems became overwhelmed, lakes drained in hours, ice shelves splintered, and glaciers that had been stable for millennia began collapsing with astonishing speed. The evidence for catastrophic meltwater pulses is found not only in ocean records, but in the very shapes of continents. In North America, the channeled scablands of Washington state were carved by megafloods from glacial Lake Missoula. These floods tore through basalt, carved coulees, and left behind immense dry waterfalls like Dry Falls, once among the largest cataracts on Earth. In Europe, the catastrophic draining of proglacial lakes reshaped the Rhine, Danube, and Volga basins. In Siberia, massive outburst floods sent water rushing northward into the Arctic Ocean, each contributing its share to global sea level pulses. The oceans recorded these events as abrupt changes. Coral reefs, which grow upward toward the sunlight, recorded rapid sea level rises in their growth patterns. During marine isotope stage 5e, for example, coral terraces in the Bahamas and Seychelles reveal sudden jumps that indicate sea levels rose multiple meters within centuries, possibly even decades during the fastest phases. Similarly, in the far older record of MIS-11, around 400,000 years ago, coral platforms show evidence of rapid, step-like rises that reflect massive sudden contributions from melting ice sheets. The climate impacts of these melt pulses extended far beyond sea level. When enormous volumes of fresh water entered the North Atlantic, they disrupted the thermohaline circulation, weakening or even shutting down the formation of deep water. This led to abrupt cooling events in parts of the Northern Hemisphere, even as global temperatures were rising, creating complex climatic whiplash that reshaped ecosystems and weather patterns. Africa experienced shifts in monsoon intensity. Asia underwent rapid changes in rainfall, and the southern oceans warmed as heat transport slowed. Each pulse was a global shockwave. For early humans, these catastrophic sea level rises shaped the world in which our ancestors evolved. Although Homo sapiens emerged only around 300,000 years ago, earlier hominin species lived through several of these pulses. Coastlines that had been dry land for tens of thousands of years vanished rapidly, drowning migration corridors, isolating populations on new islands, and forcing groups to adapt to quickly changing resources. Later, when modern humans began dispersing out of Africa, they encountered coastlines already shaped by countless glacial floods and retreats, landscapes carved by water that moved not with the calm tides of a day, but with the catastrophic surges of ages. Some melt pulses were so large that they temporarily raised sea level faster than coral reefs could grow, drowning reef systems that had survived for millennia. Others cut off land bridges like Sunda and Sahul, turning connected landmasses into archipelagos. These sudden drownings shaped the early maritime history of our species, influencing which regions humans could reach and when. Catastrophic meltwater floods are the sharpest edges of Earth's long climate rhythm, the moments when the slow, deep accumulation of ice released its stored water in pulses that reshaped continents. They were not anomalies, but essential features of the late Pleistocene system, arising from the inherent instability of massive ice sheets, the feedback loops of CO2 and ocean circulation, and the amplifying effects of orbital cycles. And each time they occurred, they left behind clues: coral terraces, isotopic shifts, submerged landscapes that allow us to trace their power across hundreds of thousands of years. By the time the last of these melt pulses created the post-glacial world we now inhabit, the pattern had become unmistakable. Earth's sea levels did not simply rise and fall, they leapt and plunged, surged and receded, responding to a climate engine capable of extraordinary violence as well as extraordinary stability. These floods were the crescendo moments of each glacial cycle, and they prepared the world for the next chapter in this long, watery story, the emergence of humans and the reshaping of their world by coasts that never stayed still for long. The human world emerged on shores that refused to stay still, and the rise and fall of sea levels across the last 3 million years shaped migration routes, ecosystems, and even the timing of human dispersal so profoundly that the story of our species cannot be separated from the story of Earth's pulsing coastlines. Long before Homo sapiens walked out of Africa, hominin ancestors, Homo habilis, Homo erectus, Homo heidelbergensis, lived in landscapes repeatedly transformed by glacial lows that exposed vast coastal plains and interglacial highs that drowned them again, turning pathways into islands and islands into continents. Every ancient shoreline shift altered food availability, changed weather patterns, redirected rainfall, and opened or closed migration corridors. For early humans, coastlines were not boundaries, they were moving forces of destiny. During deep glacial periods, when sea levels dropped as much as 120 meters below modern levels, enormous landmasses emerged. Africa expanded outward as the Red Sea narrowed to just a shallow strait, sometimes nearly closing entirely. Arabia grew wider, its coasts extending dozens of kilometers beyond their modern positions, and the Persian Gulf became a vast grassland basin fed by rivers that would one day vanish beneath the ocean. These exposed lands created migration bridges that Homo erectus used to disperse out of Africa around 1.8 million years ago, moving northward into the Levant and eastward across Arabia into Eurasia. Fossil and stone tool evidence from Dmanisi, Georgia, dating to around 1.77 million years ago, marks one of these early migrations, made possible by low sea levels and expanded, greener corridors shaped by glacial climates. Farther east, the Sunda Shelf connected mainland Southeast Asia to the islands of Sumatra, Java, and Borneo during most glacial cycles. This massive lowland, Sundaland, was larger than India at times and served as a thriving habitat for early humans and megafauna. When sea levels rose during interglacials, Sundaland fragmented into islands, isolating populations and forcing adaptations to new environments. Genetic studies showed deep splits in human and animal lineages across this region, reflecting the repeated formation and drowning of land bridges. To the south, Australia, Tasmania, and New Guinea were fused into the single continent of Sahul during glacial lows. This union created a continuous migration route from Southeast Asia into Australia, allowing Homo sapiens, much later, to reach the continent by at least 50,000 years ago. These migrations were possible only because low sea levels exposed land corridors and narrowed ocean crossings. When the ice melted and seas rose again, Sahul fragmented, stranding populations on separate islands and shaping distinct cultural and genetic histories. In Europe, Britain was not an island for most of the Pleistocene. Instead, it formed part of the European mainland, connected by the vast land bridge of Doggerland, which stretched across what is now the North Sea. This fertile plain supported mammoths, woolly rhinoceroses, Neanderthals, and early Homo sapiens. But every interglacial rise drowned Doggerland again, forcing communities to retreat to higher ground as the sea returned. The final drowning of Doggerland around 8,000 years ago erased one of the last great Pleistocene landscapes, but its story mirrors countless earlier drownings across Europe over the past million years. Africa itself experienced profound shifts. During glacial periods, the Sahara contracted, giving way to grasslands and savannas that linked North Africa to the Mediterranean and Middle East. Rivers flowed across regions that are today deserts. These wetter corridors, exposed by low sea levels and enhanced rainfall patterns, allowed hominins to migrate out of Africa multiple times, including early Homo erectus, later Homo heidelbergensis, and much later Homo sapiens. Interglacials reversed this pattern. Rising seas intensified evaporation in the Mediterranean, the Sahara dried, and corridors closed again. This pulsing green Sahara cycle synchronized with glacial rhythms, tying human migration windows directly to sea level and climate changes. The coasts did not just guide migration, they shaped early human subsistence. When sea levels rose, coastal regions became rich in shellfish, fish, seabirds, and tidal resources. Archaeological sites such as Pinnacle Point and Clayses River in South Africa show that early Homo sapiens relied heavily on marine resources during certain interglacials, especially around 120,000 years ago. Rising seas flooded river mouths, creating estuaries and lagoons that were nutrient-rich and stable food sources. These environments may have been critical in supporting expanding human populations, enabling cultural and technological developments that would later spread worldwide. When sea levels fell during glacial periods, these coastal food systems disappeared, replaced by vast inland plains. Humans adapted by shifting to terrestrial hunting and foraging, following herds of megafauna across the newly exposed landscapes. The repeated gaining and losing of coastal resources created cycles of abundance and scarcity that shaped human resilience, tool innovation, and mobility strategies. Sea level shifts also dramatically affected island ecosystems. As water rose and fell, islands merged or split apart. Isolated populations of hominins, most famously Homo floresiensis on Flores and possibly Homo luzonensis in the Philippines, emerged in regions where rising seas trapped groups on shrinking islands, triggering evolutionary dwarfing or other adaptations. These species are living proof of how intimately human evolution is tied to the pulse of coastlines. The development of symbolic culture and early seafaring also appears linked to rising seas. When interglacial floods isolated populations on islands, humans were forced to adapt or to attempt crossings. There is evidence of seafaring in Southeast Asia as early as 50,000 to 60,000 years ago, a skill almost certainly shaped by the fragmentation of island systems during rising sea levels. Without these environmental pressures, early navigation may have evolved far later. Furthermore, the spread of modern humans into the Americas was tightly bound to sea level changes. During the last glacial maximum, around 19,000 years ago, sea levels fell more than 120 meters, exposing the Bering Land Bridge and creating a continuous corridor between Siberia and Alaska. Coastal routes along the Pacific Rim also opened, providing marine-rich environments for early migrants. When the glaciers collapsed and sea levels rose, these corridors were submerged forever, preserving the archaeological mystery of the first Americans beneath waves and silt. Beyond migration, sea level pulses shaped entire cultural narratives. Many ancient flood myths, stories of drowning lands, sinking islands, and lost coastlines, may have roots in the rapid meltwater pulses that occurred during the end of the last ice age. Between 14,600 and 8,200 years ago, sea level rose nearly 120 meters, repeatedly advancing in sudden jumps that would have overwhelmed coastal settlements with little warning. The memory of these events, passed orally through generations, may have given rise to enduring stories across cultures. Even today, humanity lives in the long shadow of the Pleistocene sea level pulses. Our coastal cities occupy land shaped by the last interglacial highstands and the Holocene stabilization that followed. Our migration histories, genetic lineages, and cultural trajectories all bear the imprint of coastlines that moved like breathing lines across the map of the world. In the long arc of Earth's history, humans are newcomers, but we were born into a world sculpted by rising and falling oceans, and our earliest footsteps followed paths drawn by water's endless movement. The coasts guided us, challenged us, isolated us, and connected us. Without shifting sea levels, without the giant pulses of the past 3 million years, our species' journey would not have unfolded in the same way. The last Ice Age oscillations, spanning roughly the past 130,000 years, represent the final sharpest movements of the great climatic pendulum that had been swinging for 3 million years. And during this period, sea levels rose and fell with an intensity and speed unmatched in earlier cycles, shaping the world into the form we recognize today. These oscillations included the last interglacial highstand around 125,000 years ago, the long descent into the last glacial maximum, the catastrophic melt pulses that ended it, and the complex climatic flickers, Dansgaard-Oeschger events, and Heinrich events that repeatedly disrupted stability. Though humanity was now fully present across Africa, Eurasia, and beyond, the world they inhabited was anything but stable. Coastlines advanced and retreated by hundreds of kilometers. Marine ecosystems collapsed and reformed. Deserts grew and shrank, and entire land bridges appeared and vanished, all following the rhythm of sea level pulses driven by ice, CO2, and the deep ocean. The story begins with the Eemian interglacial around 125,000 years ago, known scientifically as marine isotope stage 5e. During this warm interval, global temperatures were slightly higher than today, by about 1 to 2 degrees, and CO2 levels hovered near 280 ppm. As a result, the great ice sheets retreated dramatically. Sea levels rose 6 to 9 meters above modern levels, and in some regions potentially even higher. Coral reefs in the Seychelles, the Bahamas, and the Mediterranean testify to shorelines now stranded well above today's beaches. Hippopotamuses wandered through parts of Europe. Forests spread across lands that are now tundra. This interglacial was a preview of the climatic state Earth may return to in the future. But the warmth did not last. Slowly, by the rhythm of orbital shifts and declining northern summer insolation, the climate began cooling again. Ice sheets re-expanded across North America and northern Eurasia. Sea levels, which had sat comfortably above modern heights, began to fall, at first slowly, then with increasing speed. By 70,000 years ago, Earth was already deep into a new glacial era. The seas had dropped tens of meters, coastlines extended far outward, the English Channel became a wide plain. Japan was connected to Asia. The South China Sea shrank into a lake-filled basin bordered by exposed ridges. Human populations, Neanderthals in Europe, Denisovans in Asia, and Homo sapiens in Africa, adapted to these shifting landscapes. Low sea levels opened migration corridors and expanded hunting grounds. Yet the descent into full glaciation would continue for more than 50,000 years, driven by falling insolation, increasing ice albedo, and declining atmospheric CO2. By 30,000 years ago, sea level was more than 80 meters lower. By 26,000 years ago, the planet reached its coldest point, the last glacial maximum, LGM. At the LGM, sea level stood approximately 120–130 meters below modern levels. Ice sheets thousands of meters thick smothered Canada, New England, Scandinavia, and parts of Siberia. Desert belts expanded across Africa and Asia. The Bering Land Bridge became a continent-sized corridor. Australia, New Guinea, and Tasmania fused into a single landmass, Sahul, while Southeast Asia's islands merged into the supercontinent of Sundaland. Coastal plains the size of countries stretched where ocean now lies. The climate was cold, dry, and windy, conditions ideal for dust production, which intensified biological drawdown of CO2 and reinforced the deep glacial state. Yet beneath this apparent stillness, the great ice sheets were preparing for collapse. Warming began around 20,000 years ago, triggered by orbital alignment and amplified by rising CO2. And as temperatures climbed, the ocean ice system entered a period of extreme instability. The first dramatic rise came during meltwater pulse 1a, around 14,600 years ago. In less than 500 years, global sea level rose 1625 meters, a rate far faster than coral reefs could adapt. Entire coastlines drowned, the Sunda Shelf flooded, fragmenting Southeast Asia into the islands we know today. The Persian Gulf filled for the first time since the previous interglacial. In the Americas, valleys and river mouths were inundated, and some of the earliest coastal settlements vanished beneath rising tides. The North Atlantic registered these surges as sudden freshening events. Heinrich Event 1, one of the most powerful iceberg surges of the last glacial termination, occurred shortly before meltwater pulse 1a, sending fleets of icebergs into the Atlantic. Their meltwater disrupted the conveyor, caused abrupt cooling in Europe, and shifted tropical rainfall belts southward. Climate whiplash accompanied sea level rise. Regions warmed and cooled rapidly, deserts expanded and contracted, and monsoons intensified or collapsed depending on the state of the ocean circulation. After meltwater pulse 1a, sea levels continued rising but at a slower pace until another surge, meltwater pulse 1b, occurred around 11,500 years ago, possibly linked to rapid collapse of the Laurentide ice sheet. During this time, the Bering Land Bridge drowned permanently, severing the final terrestrial link between Eurasia and the Americas. Coastal peoples across the world watched shorelines advance inland, sometimes tens of meters in a single human lifetime. In the Mediterranean, rising seas breached the Bosporus around 9,500 years ago, flooding the Black Sea basin and transforming it from a freshwater lake into a brackish inland sea. In Southeast Asia, rising water severed the last land cords connecting the continental shelf fragments into isolated islands. Amid these surges, Earth experienced abrupt climate oscillations known as Dansgaard-Oeschger (DO) events, rapid warming episodes followed by slower cooling phases, recorded in Greenland ice cores as temperature jumps of 8 to 15 degrees Celsius within decades. Each DO event altered atmospheric circulation, reshaped precipitation patterns, and changed sea surface conditions. Though these events did not directly drive major sea level rises, they influenced the pace and timing of melting by altering regional temperatures and feedback loops. Heinrich events, 6 major ones during the last glacial period, were another form of ice sheet instability. Each involved the massive discharge of icebergs from the Laurentide into the North Atlantic, enough to cover the ocean surface with layers of ice-rafted debris. These events cooled the North Atlantic drastically, disrupted deep water formation, and set the stage for the next warming rebound. Sea level signals from these events are subtle but detectable, small pulses that reflect the relationship between ice sheet collapse and ocean circulation. By 12,000 years ago, humans were everywhere, across Africa, Eurasia, Australia, and the Americas, and they lived in a world being reshaped violently by melting ice. Coastal settlements were repeatedly lost, migratory routes submerged, islands formed where none had existed for tens of thousands of years. Humans adapted by shifting inland or upward, developing new fishing technologies, cultivating coastal resources, and building early maritime identities. By 8,200 years ago, another abrupt event occurred, the 8.2 Ka cooling event, triggered by the final drainage of glacial Lake Agassiz Ojibwe into the North Atlantic. This flood temporarily slowed the conveyor and cooled the northern hemisphere for several centuries, though sea level rise at this stage was nearing completion. By roughly 6,000 years ago, sea level stabilized close to its modern position, ending the wild oscillations of the Pleistocene and creating the coastal world in which agriculture, cities, and complex societies would eventually flourish. The last ice age oscillations therefore represent the culmination of 3 million years of sea level pulses, sharp, fast, devastating, and transformative. They shaped human migration, reshaped continents, and created the ocean margins that define our world today. With the Holocene stabilization, humanity inherited a rare moment of sea level calm, a pause in a story otherwise defined by relentless movement, astonishing instability, and the long glacial heartbeat of a planet sculpted by ice. Holocene stabilization marked the end of Earth's great 3 million year sea level drama, a rare quieting of the climatic heartbeat that had pulsed through the Pleistocene in great glacial swings. And as the last of the super ice sheets melted, seas stopped their relentless advance and settled into a remarkably narrow range, allowing human civilization to take root along coasts that, for the first time in ages, remained stable for thousands of years. This period, beginning roughly 11,700 years ago with the end of the Younger Dryas cold snap, ushered in a warm, stable climate in which atmospheric CO2 hovered around 260–280 ppm, temperatures moderated, rainfall patterns steadied, and most importantly for humanity, sea levels slowed their rapid climb and approached a near-steady state around 6,000 years ago. For a species that had always chased shifting shorelines across exposed shelves and drowned valleys, the sudden stillness of the oceans was unprecedented and transformative. The Holocene began with one final burst of climatic turbulence. The Younger Dryas, lasting from about 12,900 to 11,700 years ago, had briefly plunged the North Atlantic back into near-glacial conditions after a massive meltwater flood disrupted the ocean conveyor. Sea levels continued rising during this period, but the pace was uneven. Pulses of rapid ascent alternated with pauses as ice sheets responded to shifts in ocean circulation and atmospheric forcing. Yet once the Younger Dryas ended, temperatures rebounded quickly across the northern hemisphere. The Laurentide ice sheet, the last continental giant, collapsed in a series of final retreats. Its remaining remnants in Canada disintegrated, releasing meltwater that contributed to a final but diminishing series of sea level increments. By 10,000 years ago, global sea level was about 40 meters below modern levels. Coastlines were still expanding inland, river mouths flooding, deltas forming anew. But the pace of rise was slowing as the ice supply dwindled. By 8,000 years ago, sea level was within roughly 15 meters of today. Coral reefs that had been racing upward to stay near sunlight began to stabilize. Lagoons formed behind reef crests, estuaries widened, and mangrove forests spread along coastlines that were rapidly taking on their modern form. Around 6,000 years ago, give or take depending on region, sea level effectively stabilized within a few meters of present height. This stabilization was not perfect. Slight fluctuations occurred due to glacial isostatic adjustment, as land once depressed by ice slowly rebounded upward, ocean current changes, and local tectonics. But globally, the Holocene was extraordinarily stable by Pleistocene standards. For the first time in human evolutionary history, coastlines became predictable, allowing permanent settlements to flourish along river deltas, bays, and estuaries without fear that the sea would suddenly reclaim them. This stability was essential for the rise of agriculture. The earliest farming cultures in Mesopotamia, the Nile Valley, the Indus River Basin, and the Yellow River region emerged between 10,000 and 7,000 years ago, as sea level rise slowed and floodplains became stable, fertile, and seasonally predictable. Had the seas still been surging upward at rates of meters per century, early farmers would have struggled to maintain fields, storage pits, and irrigation canals. Instead, the Holocene offered a quiet stage on which domesticated plants and animals could spread, transforming human societies from nomadic bands into settled communities. Rivers responded to this stabilization as well. With coastlines no longer racing inland, river mouths settled into steady positions. Deltas expanded into broad, fertile fans. The Nile Delta, the Tigris-Euphrates marshlands, the Ganges-Brahmaputra Delta. These landscapes became population centers precisely because the sea had stopped its relentless advance. In earlier epochs, such deltas, the interface between land, river, and sea, would have been unstable, repeatedly drowned and re-exposed by rising and falling oceans. Human culture blossomed in this coastal calm. Fisherfolk established consistent harvest cycles along estuaries and beaches. Trade flourished as predictable coastlines enabled maritime journeys. By 5,000 years ago, complex societies from Egypt to Sumer to the Harappan world depended on coastlines with forms recognizable today. Written languages, monumental architecture, and long-distance trade all emerged in a world whose geography no longer shifted beneath humanity's feet. Yet the Holocene was not merely a time of human flourishing. It was also a time when Earth continued adjusting to the end of the Ice Age. As ice sheets melted, the crust beneath them rose slowly in a process known as post-glacial rebound. This caused regional sea level differences. Parts of Scandinavia and Canada rose meters higher, while other regions experienced slight local sea level increases as land subsided. These local changes left complex archaeological signatures, ancient shorelines now perched far inland in Scandinavia, while other regions saw ancient coastal sites now submerged offshore. Climate continued to fluctuate modestly as well. The Holocene thermal maximum, roughly 9,000 to 5,000 years ago, brought slightly warmer temperatures than today in many regions, allowing forests to expand northward and monsoons to strengthen. Later, minor cooling events, the 4.2 kiloyear aridification, the Roman Warm Period, the Little Ice Age, left imprints on human history, but caused no significant global sea level shifts. Compared to the vast pulses of the Pleistocene, these changes were gentle ripples. Marine ecosystems stabilized dramatically. Coral reefs, which had been racing upward throughout the Pleistocene to keep pace with rising seas, now expanded outward instead, building broad platforms and supporting diverse marine life. Mangrove forests stabilized coastlines, creating nurseries for fish. Seagrass meadows expanded across shallow bays formed by the near-still seas. Many of these ecosystems, fragile yet productive, owe their success to the stability that the Holocene provided. Another profound consequence of sea level stabilization was the preservation of cultural memory. Unlike earlier humans who lived through catastrophic drownings of coastal plains, Holocene peoples saw coastlines as enduring features. They built harbors, villages, and temples near the shore. They mapped the coasts, named them, and tied their identities to them. The fact that these coastlines would remain stable for millennia allowed civilizations to view the ocean not as a chaotic agent, but as a boundary, a highway, a provider. Still, echoes of the Pleistocene linger. Submerged river valleys, now continental shelf features, remind us of a time when sea level lay far lower. Drowned forests off modern coasts preserve the memory of landscapes lost during the early Holocene rise. And cultural flood myths, from Mesopotamia to Polynesia, may preserve ancestral recollections of rapid seawater advances during meltwater pulses that preceded the Holocene stabilization. In this long story of sea level change, the Holocene is the rare intermission, the moment when the orchestra rests between movements. For 3 million years, Earth's oceans rose and fell in giant pulses, sculpting continents, ecosystems, and evolutionary pathways. But once the Holocene began, the seas settled into place, granting humanity a peaceful shoreline on which to build everything from the first farms to the world's largest cities. This calm, though extraordinary in geological terms, is not permanent. It is simply a pause in the planet's long rhythm. But during this pause, this brief golden window, human civilization took shape, flourished, and spread across the world, unaware that the quietness of the coastline was the most precious gift the earth had ever offered. The long memory of water carries across ages, and as we reach the final turn of this 3 million year story, we see that the giant pulses of rising and falling seas did not simply sculpt ancient shorelines. They shaped the continents we walk on, the ecosystems we depend on, and the world that humanity inherited during the brief calm of the Holocene. Though the great glacial cycles have paused, their fingerprints lie everywhere. In drowned river valleys beneath today's coastlines, in coral terraces uplifted far above modern tides, in the submerged shelves that once held forests and herds, and in the myths of floods and lost lands that echo through human memory. The water remembers, even when we forget. And this memory whispers a profound truth. The stability we know today is not the norm. It is the exception, a rare and precious interlude in a planet defined by motion. To understand the long memory of water, we first recognize that sea level is not simply the measure of where the ocean meets the land in a given year. It is a record of Earth's deepest rhythms, orbital cycles, ice sheet breathings, atmospheric chemistry, and the dance of heat within the oceans. Each shoreline carved in stone, each coral terrace stranded above the surf, each submerged canyon on the continental shelf is a page in this memory. Together, they form a chronicle of the last 3 million years, a chronicle in which sea level rose and fell not randomly, but in giant pulses, responding faithfully to the heartbeat of the climate system. The geological evidence is overwhelming. Submerged coastlines stretch hundreds of kilometers offshore, revealing where the sea once lay when ice sheets grew to continental scales. At depths of 40 meters, 80 meters, 120 meters, underwater explorers map ancient shorelines, some carved during the last glacial maximum, others during older cycles long forgotten. River valleys cut deep into these submerged landscapes, betraying the paths of rivers that flowed across plains now drowned beneath waves. In some regions, forests remain preserved underwater, their stumps still rooted in soils that once held thriving ecosystems. These features record the downward strokes of sea level lows. Above today's sea level, stranded coral terraces rise like giant staircases. In places like Barbados, Papua New Guinea, and the Seychelles, each step reflects a time when the seas paused during an interglacial highstand, some hundreds of thousands of years old, some more than 1 million. These terraces are not simply fossils of warm periods, they are fossilized moments of climate triumph, times when the ice sheets had melted enough to surrender water back to the oceans. Together with submerged features, they form a double record, one above, one below, capturing the full sweep of sea level memory. This memory is not only geological but Ecological. Species distributions today still reflect the comings and goings of ancient shorelines. Mangrove forests, seagrass meadows, coral reefs, and coastal wetlands are shaped by the Holocene stabilization, but rooted in patterns set during countless earlier rises and falls. Some species evolved on exposed coastal shelves during glacial lows and retreated uphill when seas returned. Others survived only in refuges as sea level pulses redrew continents. The biodiversity of Southeast Asia, for example, owes its labyrinthine structure to repeated cycles of expansion and fragmentation as Sundaland grew and shrank. Likewise, the formation of island arcs across the Pacific, the Caribbean, and the Mediterranean reflects ancient sea level rhythms. Human history, too, bears these imprints. The shaping of migration routes, the position of ancient settlements, and even the origins of agriculture were determined by where the seas chose to stand during key moments in the Holocene. The Persian Gulf Basin once hosted fertile river systems before rising seas drowned it. The English Channel, now a watery divide, was once a vast plain crossed by mammoths and early humans. Doggerland, Atlantis-like, lies beneath the North Sea, holding secrets of Mesolithic hunters who lived on land now hidden by water. The long memory of water preserves our forgotten landscapes, waiting for archaeologists to rediscover them. But perhaps the deepest lesson in this memory is what it tells us about the future. The calm of the Holocene, this rare period in which sea level remained within a narrow band, allowed humanity to flourish. Our ports, cities, and cultural heartlands cluster along coastlines frozen in place for nearly 6,000 years. Yet the forces that kept seas stable did not disappear. They are merely resting. Orbital cycles continue their slow drift. Ice sheets still hold vast volumes of stored water, and the ocean conveyor still pulses beneath the surface, shifting heat across the globe. The memory of the past reveals the latent power of these systems. In earlier eras, a slight shift in summer sunlight or CO2 concentration could unleash tens of meters of sea level rise. Massive ice sheets advanced and retreated with little regard for the land masses they drowned or exposed. Continental shelves were alternately grasslands and sea floors. The lesson is clear. Earth's seas are not fixed boundaries, but dynamic edges of a world constantly reshaped by climate. The memory of water also warns us that stability is fragile. During the Pleistocene, feedbacks between CO2, ice, and ocean heat determined whether sea level rose gently or surged catastrophically. In recent centuries, human activities have begun altering these same feedbacks at a pace unprecedented in geological time. Although this story does not dive into the modern era, the ancient rhythms remind us of what the ocean is capable of when climate forcing increases rapidly. We know from coral terraces and meltwater records that ice sheets can collapse quickly once thresholds are crossed. We know from submerged plains that sea level can rise meters within centuries. The memory of water is not only a window into the past, but a mirror reflecting possibilities for the future. And yet there is wonder as well. The long record of sea level pulses shows a planet alive, responsive, and beautifully complex. It shows continents breathing with ice and ocean, expanding and contracting in rhythms far older than humanity. It shows ecosystems rising, falling, adapting, and thriving across shifting coasts. It shows our own species emerging in a world sculpted by water, a world that challenged, shaped, and guided our ancestors at every turn. As we close this story, imagine a vast shoreline, not the one you know, but one that stretches thousands of kilometers farther than today, or one that lies deep beneath warm waves. Imagine forests standing offshore, coral terraces perched above, rivers crossing plains long drowned. These are Earth's old coastlines, its lost boundaries, its long memories written in stone and sediment. They whisper the same message across millions of years. Nothing stays still. Not ice, not climate, not the sea. And yet within that movement, life adapts, endures, and evolves. The story of why sea levels rose and fell in giant pulses for 3 million years is, in the end, the story of a restless planet, one that breathes through water, one that remembers every rise and fall, and one that still holds the power to reshape the world we know. The ocean is not simply a backdrop to Earth's history. It is the storyteller, the witness and the force that carved the path from ancient ice to the human age.